A commercial aircraft cruising at high altitude is continuously subjected to the chaotic kinetic energy of the atmosphere. When a severe gust strikes the airframe, it delivers a massive, asymmetrical shearing force. This singular impact induces two simultaneous geometric disruptions: a directional yaw, which drives the nose left or right, and a lateral roll, which banks the wings up or down. To survive these persistent disturbances, the airframe must possess a natural geometric tendency to return to straight and level flight entirely on its own, without requiring continuous pilot input. This animated 3D diagram illustrates the primary metric for measuring that disturbance. When a lateral gust shifts the oncoming relative wind off the aircraft's center axis, it creates what is known as a side slip angle, denoted by the Greek letter beta. To correct the yawing motion around the vertical z-axis, the aircraft relies on static directional stability. This is the aerodynamic response that automatically rotates the nose back into the oncoming wind. Simultaneously, to correct the rolling motion around the longitudinal x-axis, the aircraft relies on lateral stability. This is the aerodynamic response that levels the wings parallel to the horizon. This introduces a strict engineering paradox. We must build an airframe stable enough to reject violent atmospheric disturbances passively, yet we must also equip it with directional control system at exact same stability when a maneuver is required. Designing an aircraft is a high-stakes mathematical tug-of-war. Every surface is a compromise between the physics of equilibrium and the required control authority of the pilot. This top-down orthographic diagram isolates the directional axis, removing roll from the equation. The target icon marks the center of gravity, or CG, the exact 3D pivot point around which the entire aircraft's mass is balanced. When a side slip occurs, the surface area of the fuselage ahead of the center of gravity acts as a destabilizing sail. It catches the relative wind and attempts to push the nose further away from the intended flight path. To counteract this destabilizing forward fuselage force, engineers rely on the vertical stabilizer at the rear of the aircraft. The effectiveness of this tail relies on two primary geometric levers: the total surface area of the vertical tail, designated as S sub v, and the length of its moment arm, the exact distance from the center of gravity to the tail's aerodynamic center, designated as L sub v. When the aircraft enters a side slip, the incoming wind hits that vertical tail. This generates a lateral lift force, pushing the aft section away from the wind and rotating the nose back to center, much like a weathercock aligning with the breeze. This equation defines the yawing moment derivative, Cn beta. It serves as the non-dimensional mathematical metric for this weathercock stability, calculating exactly how much restorative turning force is generated per degree of side slip. For an aircraft to possess positive static directional stability, this equation must satisfy a strict criterion. The yawing moment coefficient must increase positively as the side slip angle increases. In mathematical terms, Cn beta must be greater than 0. If an engineering flaw results in a negative Cn beta value, the consequences are catastrophic. The moment the aircraft is disturbed by a gust, the aerodynamic forces would drive the nose further away from the wind, causing the airframe to actively try to fly backward. A positive Cn beta guarantees the nose will naturally track the relative wind. However, analyzing yaw in a strictly two-dimensional vacuum ignores the physical reality of flight. Correcting a side slip inevitably induces a simultaneous roll. This head-on diagram shifts our perspective to isolate the lateral rolling dynamics along the longitudinal axis. Notice the pronounced upward angle of the wings extending from the fuselage. This upward tilt from the wing root to the wingtip is defined as the dihedral angle, represented by the Greek letter gamma. Introducing a side slip completely alters how the oncoming air flows over this specific V-shaped geometry. When the aircraft banks and slips sideways, the dropped leading wing engages the oncoming air at a sharper incline. It experiences a higher local angle of attack, the angle between the wing's chord line and the relative wind, compared to the shielded trailing wing. This difference in angle of attack creates asymmetric lift. The dropped wing generates significantly more upward force than the trailing wing, creating a rolling moment perfectly designed to push the dropped wing back up to a level orientation. This equation calculates the rolling moment derivative, Cl beta. It is the exact metric used to quantify this restorative lateral force, commonly known as the dihedral effect. The mathematical requirement for lateral stability dictates that the rolling moment coefficient must be negative for a positive side slip angle. Therefore, CL beta must be less than 0. Modifying these values reveals an inherent, unavoidable coupling between the two axes. Altering the wing dihedral to adjust lateral stability changes the directional dynamics. Conversely, scaling the vertical tail to fix directional stability directly impacts the lateral roll. Calibrating CN beta and CL beta correctly yields an airframe that naturally wants to fly straight and level. But this extreme passive rigidity creates a massive physical obstacle when the pilot actually needs to alter the flight path. The passive stability of the airframe is only the baseline. Flight dynamics must also account for the active, intentional forces of directional control commanded from the cockpit. This diagram isolates the rudder. When deflected, it generates a turning force, quantified by the rudder control power derivative, Cn delta R. This metric defines the pilot's total mechanical authority to command yaw. Engineers size the rudder to survive worst-case asymmetric boundary conditions, far exceeding the requirements for a smooth, coordinated turn. The first and most severe design constraint is the one-engine inoperative, or OEI scenario, specifically during a high-power takeoff. If a wing-mounted engine violently fails, the opposite engine continues to blast thrust at maximum power. This asymmetric thrust generates a massive, uncontrolled yawing moment, violently dragging the nose toward the dead engine. To prevent a crash, the rudder must be large enough to generate a restorative countermoment, capable of completely overriding that engine asymmetry. This dictates the aircraft's minimum control speed, or VMC. This is the absolute lowest airspeed where the moving air still provides enough dynamic pressure, kinetic energy over the rudder surface, to hold the aircraft straight against a failed engine. The second major constraint driving rudder size is the necessity of executing crosswind landings. When approaching a runway with a heavy lateral wind, pilots utilize a technique called crabbing. They induce a deliberate side slip, flying the aircraft slightly sideways to track straight down the runway center line. In the final seconds before the tires touch the tarmac, the pilot requires immense rudder authority to violently kick out this crab angle and instantly align the heavy landing gear with the runway geometry. The third boundary constraint is the constant aerodynamic necessity of counteracting adverse yaw. This 3D diagram shows the aerodynamics of roll initiation. To bank the aircraft, the aileron on the rising wing deflects downward, increasing lift. However, this creates excess-induced drag, creating a force vector that pulls backward, directly opposing the direction of the turn. The pilot must utilize the rudder to overpower this specific drag penalty, forcing the nose to track smoothly into the turn rather than dragging away from it. Directional control authority provides a survival mechanism designed to brute force the aircraft through extreme asymmetric regimes, moving the airframe far beyond the needs of routine flight. During flight, the pilot isn't solving for one variable at a time. They continuously manage yaw, roll, and control inputs in a highly dynamic environment. The functional relationship is clear. Static stability ensures that the airframe naturally wants to fly straight, while directional control gives the pilot the mechanical power to dictate exactly where straight is. This presents flight dynamicists with the ultimate optimization trap regarding the Cn beta derivative. If engineers increase passive stability too much, the vertical tail becomes a massive liability during an engine failure. The tail will sense the pilot's defensive yaw input as a disturbance, and it will aggressively fight the pilot's inputs to maintain its own equilibrium. This split-screen diagram illustrates the proportional engineering rule. Any increase in geometric stability mathematically mandates a proportional increase in rudder size and control authority. But bolting larger control surfaces onto the airframe inevitably adds weight and drag, severely penalizing the overall fuel efficiency and range of the aircraft. Analyzing these non-dimensional derivatives, mapping out exactly how Cn beta, Cl lambda beta, and Cn lambda delta beta interact, is the only empirical way to guarantee a prototype is safe and flyable before it ever leaves the runway. Mastering directional and lateral stability is a zero-sum game. It requires engineers to calculate the exact mathematical razor's edge between the absolute safety of natural equilibrium and the strict necessity of total pilot control.